For our next molecule, let's take a look at a dihydroxy substituted benzene. So let's put a hydroxyl substituent at the 1 position and also one at the 4 position. This molecule is 1,4-dihydroxybenzene, and we might also recognize it as the reduced form of the compound 1,4-benzoquinone. Let's kind of show what 1,4-benzoquinone looks like. So this is 1,4-benzoquinone, and it's relatively easy to reduce the benzoquinone to the dihydroxy form, and likewise to oxidize the dihydroxy form to the benzoquinone. So for the time being, we're going to confine our attention to the dihydroxy derivative, and we would like to classify it as to its point group symmetry. As we've been doing rather regularly, the first thing we want to look for is a high order rotation axis, and typically we're looking for that in the plane of the board, so that our dowel becomes the axis of rotation in the z-axis. And we notice that while we no longer have a C3 or a C6 rotation, we can rotate the molecule by 180 degrees, and the molecule will line up. The oxygen will go to oxygen, hydrogen will go to hydrogen, and all the carbons of the rings will go to other carbons. So we see that this molecule actually has a C2 rotation. And the C2 rotation is in the z-axis, so we maybe just noted that, call it C2Z. Let's see if it has any other C2s that might be perpendicular, normal, to this high order rotation axis. So the reason why we're doing that is we want to determine if we have a D group of some sort. One of the possible axes that we might investigate is along the x-axis, like so, and we notice that if we rotate by 180 degrees, most of it will line up. The oxygen will go to oxygen, but then this hydrogen here would come to this side, and we see that the hydrogen is actually on the other side, so that we do not have a C2 around this particular axis. Again, we might try the y-axis as a possible axis of rotation for a C2. And again, we have the same problem that if I do a C2 rotation, it's going to take the hydrogen here and put it over here, but there isn't a hydrogen there already. So therefore, we don't have a C2 about the y-axis. The only rotational axis that's non-trivial that we have is this C2Z. But we do have some other things going on here. One of them is we recognize in the plane of the board that this 1,4-dihydroxybenzene is a planar compound, and therefore it is has a mirror plane in the plane of the board. So almost we can fillet it, and the top would be exactly like the bottom. So we do have a mirror plane, and we notice something also about the mirror plane is that the mirror plane is normal, perpendicular to the high order rotation axis. So that tells us that we have a sigma H. We have a horizontal mirror. So we know that we have the identity because we always have the identity. As I like to say, it's the Rodney-Dangerfield of symmetry operations. But the definition of a group, it's an essential feature of any group. We have a C2, we have a sigma H, and we have one additional symmetry operation, which we can find if we highlight the center of the molecule, so to speak, with a green dot. We notice that if we draw a vector from the green dot to any particular atom, measure that distance, if I go in the opposite direction, the identical distance, I will reach an identical atom. So if I go here to a carbon atom, go in the opposite direction, the same distance, I'm also going to find a carbon atom. If I go from the green dot to the oxygen atom and go the same distance in the opposite direction, I also hit an oxygen atom. This tells us that I have the group, the symmetry operation of inversion. And with these for symmetry operations, I can recognize, I didn't need to find the inversion, but I know it's there. I can classify this as point group C2H. Let's look for some more interesting substitution patterns so that we might classify our molecule. Another one which we can ascertain is the following. So I can substitute it with iodine. So iodine I'll put up here. I have chlorines at these positions. And fluorine at the remaining positions. So this is a very highly substituted benzene derivative. And I want to determine what the point group symmetry of this particular molecule is going to be. Well, the first thing I want to look for is a high order rotation axis. So I notice that if I look for my axis here, that if I rotate by 180 degrees, it will take iodine to iodine, fluorine to fluorine, and chlorine to chlorine. So I certainly have a C2 axis. And it's a C2Z, just if you want to classify it by the axes involved. So we have this particular thing. Let's see what else we have. We have, well, the other thing we want to look for is we want to look for C2 axes. So particularly look for a C2 axis that is going to be perpendicular to the high order rotation axis. So we might try something along the y-axis, for example. And we notice that this works quite well for the iodines, but it would take chlorine into fluorine and fluorine into chlorine, so that doesn't work. So I do not have a C2 along the y-axis. I can also try along the x-axis. If I do this, it would take chlorine to fluorine, so it doesn't work. Now we might try, okay, well, I'll be clever and make it sort of diagonally here, and I can put it through the chlorines, and I notice that, well, it works well for the chlorines, but it would take fluorine into iodine, so it doesn't work. And it turns out that we don't have any C2s that are perpendicular to the high order rotation axis. In fact, we have no other C2s at all. So we don't have C2s. So let's see what other symmetry operations we might have. We might recognize, since we have a planar molecule, we suspect that we have the inversion operation, and we do. And last but not least, again, if we draw a central point here, we notice that going in opposite directions, equidistant from the center, if I go in this direction, I get fluorine. If I go in that direction, I get fluorine. And likewise, if I do that for any of the particular elements that constitute this compound, this will work. So this tells me that I have inversion. So I have the identity, I have a C2, I have a sigma H, I have a mirror plane that's perpendicular to my high order rotation axis, and I have inversion. So again, we see yet another example of the point group C2H. So now taking this particular compound, let's make a very small change into the substitution pattern and see if that will have any changes in the overall point group symmetry. And the change we're going to make is to swap the positions of the fluorine and chlorine atoms over here. So let's just swap those. So I'm going to put the fluorine here and the chlorine down here. And we want to see if this has changed the point group symmetry, and if it has, how it has. But let's look for high order rotation axes if we can. And typically we look for one in the plane of the whiteboard, and that would take iodine to iodine, but would also take chlorine to fluorine. So there is no C2 in the plane of the board, there's no C3, there's no C6. Nothing but the identity in the plane of the board. So let's see if we can find any other interesting rotational axes throughout the molecule. Well, I might notice that if I take the y-axis here, that's going to give me a C2 because it's going to rotate fluorine into fluorine, chlorine into chlorine. So I do have, about this particular axis, I do have a C2. So there is at least one C2, and that's in the y direction. Do I have any other C2s? Well, let me just try. Think, oh, well, maybe I have one along the x-axis. Okay, let me try that. But if I did that, it would take iodine to iodine, that's right. But it would take chlorine into fluorine, which doesn't work. So therefore, the only C2 I have is this C2 about the y-axis. We know we have the identity, so the next thing, having looked for the high order rotation axes and only found one, we want to start looking for mirrors. We know that we have a mirror in the plane of the board because we have a planar molecule. But notice that this particular plane includes the rotational axis. It's not perpendicular to it. So therefore, this particular mirror, the plane of the board, is going to be a vertical mirror. So it's a vertical mirror. And we also notice, kind of the left-right symmetry of the molecule, that we also have a mirror that would reflect the left side of the molecule into the right side. Again, since the rotational y-axis is in the plane itself, this is the YZ plane, we have another vertical mirror. So we notice that we have the identity, we have a C2, and two vertical mirrors. It tells us that now, by making that substitution change, we now have the point group C2V. And an important thing to notice is that this particular molecule no longer has the inversion, so it's not centrosymmetric. So if we were to have two containers of pure compound, of the previous compound and this compound, we could easily distinguish the two because the former compound was centrosymmetric and this particular compound is not centrosymmetric. Demonstrate one more benzene substitution to see its effect. So this may be one of the most complicated ones that we've done so far. So let's put a bromine at the 1 position. Let's put chlorine at the 2 position. We'll put fluorine at the 3 position. And iodine, last but not least, at the 4 position. I've deliberately assigned these substituents so that they're in alphabetical order, so I can have the 1 bromo, 2 chloro, 3 fluoro, 4 iodo benzene. And now that we've had that, this mnemonic, we'd like to be able to ascertain its point group symmetry. We notice that if I try to look for a high order rotation axis in the plane of the board, there is none other than the identity. If I look for C2s along the x-axis, it doesn't work. Along the y-axis, it doesn't work. If I look on some diagonal, it doesn't work. So we see that we have no C2s, no C3s, no C6s. The highest order rotation axis is merely a C1 from the identity, the trivial operation. So we start looking for other symmetry operations. We notice that we have a planar molecule. So we'll have a mirror in the plane of the board. So we notice that we have E, and we have a mirror. We don't have the identity, or we don't have the inversion. We definitely have identity. We don't have inversion. It's a non-centrosymmetric molecule. Just to show that quickly, if I go in this direction to chlorine, if I go in the opposite direction, there's no chlorine there. So there's no inversion. So the only two symmetry operations that this molecule possesses are the identity and mirror. So that tells us that this alphabetical compound has the point group symmetry CS. S being for Spiegel, the German word for mirror. CS. S being for Spiegel, the German word for mirror. Here again we have the more formal structure for benzene, showing all the atoms that constitute the molecule, if we were to take this structure and remove one of the carbons and its attached hydrogen and replace that with a nitrogen atom and its lone pair, we would end up with a new resonance stabilized aromatic compound called pyridine. Pyridine is of enormous importance in both organic chemistry and as a ligand in inorganic chemistry. Typically, we take the structure and in a similar manner to what we do with benzene, we tend to write it this way. We use a shorthand. It looks very much like a benzene ring, except at the top corner we show nitrogen instead with its lone pair. And again, there are 5 hydrogen atoms that are attached to carbons, which are not explicitly depicted. We would like to ascertain the point group symmetry of this important compound. Let's kind of show that how we spell pyridine. And typically in inorganic chemistry, we abbreviate it as PYR. Inorganic chemists love abbreviations. So let's figure out the point group symmetry of this molecule. We might suspect that we can treat it like benzene. It's a completely flat planar molecule. So we might look for a rotation in the plane of the board. But if we do that because of the nitrogen atom, no matter how we rotate it, other than 360 degrees, nitrogen would be taken to one of the carbon positions. Therefore, the highest order rotation axis is only a C1 in the plane of the board. But we can find another interesting rotational axis along the y-axis here. So if we look along this particular axis, kind of draw where this goes. So along the y-axis, we do have a C2 around this axis. Let me just call it C2y for the time being. So there is the high order rotation axis for this particular molecule is going to be a C2. Since pyridine, like benzene, is a planar molecule, there will be a mirror plane in the plane of the board. Notice that since it includes the C2, this particular mirror is not going to be a horizontal mirror, it's a vertical mirror. And we have one additional mirror plane, which reflects the left half of the molecule into the right. I can kind of denote it with my metal ruler here, where this particular plane would be. So therefore, we have the identity, a C2, and 2 vertical mirrors, which tells us that we have point group C2V. We can make even more complex structures using the benzene ring as our building block. And one of the first ones that we can build is formed by having 2 fused rings together. So we often write it this way. Whereas benzene has 6 carbons, these 2 rings fused together along one side have a total of 10 carbons. And this particular important compound is called naphthalene. And naphthalene has been used to kill moths. So moth flakes used to be made out of naphthalene. So we like to ascertain the point group symmetry of this particular compound. So we can look for a high order rotation axis. We might look in the center of one of the rings, but then after any rotation we have the ring from this side to that side, and there's nothing there right now. So the interesting point as far as rotation goes is actually the midpoint of the common side. Now if we rotate here, we would actually take, if we go by 180 degrees, so 180 degrees, we actually have a C2Z pivoting, and it will line up. So we do have a C2 high order rotation axis in the plane of the board. Do we have any other C2s? Yes, we do. We notice that if we go along the x-axis, I can rotate, and again, this is going to be a planar molecule, perfectly flat. I can flip it over like a pancake, and I would get a molecule that looks exactly the same. So along the x-axis, we also have a C2. So I'll call that C2X because it's along the x-axis. And last but not least, if I draw the y-axis, I notice that if I rotate about that particular axis, it would take the right ring into the left ring, and the left ring into the right ring. So I also have a C2 about the y-axis. So I have three mutually perpendicular C2 axes. So I can declare, for the time being, that the C2Z, the one about this particular axis, is going to be my high-order rotation axis. And I found two other C2s that are perpendicular to it. So that tells me immediately that I have a D2 group of some type. So you get to 2 because of the C2 being the high-order rotation axis. It turns from a C to a D because we found C2s that are perpendicular to it. We also have a number of mirrors for this compound. The first one, this is the key mirror to find as far as identifying the point group, is the plane of the board. Since the plane of the board is perpendicular, it's normal to the high order rotation axis, that tells us immediately that we have a horizontal mirror, and therefore this belongs to point group D2H. If you're worried that you'd like to declare one of the other C2s to be the high order rotation axis, you will find that there are sufficient other mirrors in the compound, there's a mirror there and a mirror there, that are also perpendicular to that high order rotation axis. So when we have mutually perpendicular C2s, we are free to choose any one of them as being the high order rotation axis. It will make no difference in the point group classification. Not only can we have two benzene rings that combine to form a compound, we can have any number of these. So I'll show one of the examples, the more complex examples, where we have 3 rings combined. And this is a compound called phenanthrene. And phenanthrene is a member of a class of compounds which are typically abbreviated as PAHs. And the PAH stands for polynuclear aromatic hydrocarbons. And the nuclear part refers to the ring. So since it has 3 rings, it's polynuclear. So we would like to ascertain the point group symmetry of this particular molecule. So again, typically when we see benzene rings, and we know that this compound is also perfectly flat, we look for a rotation in the plane of the board. That's usually where the high order rotation axis is most likely to be, because that's where it is for benzene itself. If I try to do a rotational axis through here, none of them will line up. So you can convince yourself of that, that if you rotate, the only rotation that will line up again will be a C1, the identity. So now we look for rotational axes that are not in the plane of the board. And the one that we'll find is along this line here. So if we go along this particular axis, we actually have a C2 axis. So there is a C2 high order rotation axis. So we'll take this ring into that ring, and then part of this ring into that part. So we do have a C2. We also have a mirror in the plane of the board. And we have a mirror plane along this line, and then coming out in a Z direction. So we recognize that we have the identity, we have a C2, and 2 sigma V's. That's a sure sign that we have the point group C2V. One other thing which is not related specifically to symmetry, but is of chemical importance, for these polynuclear aromatic hydrocarbons, that many of these compounds are implicated as causing cancer. Ultimately, they don't cause cancer directly, but in the process of being metabolized by the body, they are converted into compounds which can cause cancer. And as far as structure-activity relationships, the ability to look at the structure of the molecule and predict whether it's going to be dangerous or not, one of the key features that is a cause of concern for any compound is this particular type of region here. We notice it's the sides of the hexagons, of the rings, form a somewhat almost enclosed empty area. It's like the bay of the ocean comes in here, and here is a bay, as far as from geography. And so based on that, we actually call this type of region in a molecule the bay region. And typically, molecules that have such a bay region are likely to be of concern as far as causing cancer. So typically, phenanthrene is not one of the more dangerous compounds, but as we add more rings, get the larger polynuclear aromatic hydrocarbons. Those particular compounds are often very, very serious carcinogens, especially when they have one or more of these bay regions. So let's show one last example of a polynuclear aromatic hydrocarbon that has a bay region, and also let's attempt to ascertain its point group symmetry. So the most complicated one we're going to do in this particular episode has 4 rings. It's a 4-ring system. And this particular polynuclear aromatic hydrocarbon is called Chrysene. We would like to ascertain its point group symmetry. Let's look for high order rotation axes. If I start at this particular point, I've judiciously chosen it ahead of time, and I notice if I rotate about this point, that this region up here will map into this region here, so that in the plane of the board I have a C2. So I have a C2Z for this particular molecule. Do I have anything else? Well, I know that I have the identity, and these polynuclear aromatic hydrocarbons are generally planar, so this molecule is planar. There's a mirror in the plane of the board that happens to be perpendicular to the high order rotation axis, which tells me that I have a horizontal mirror. Just from those facts, I can immediately classify this molecule as belonging to the point group C2H. As one other extra bit of verification, we recognize that in the point group C2H, the 4th symmetry element, which you don't have to find necessarily, but we know has to be there, is the inversion. So starting at this particular point, I notice that if I go in any particular direction to an atom, if I go in the opposite direction, so here we go to carbon, if I go in the opposite direction, I also hit a carbon. So we see that the molecule Chrysene is a centrosymmetric molecule. Last but not least, from the chemical point of view, I see that I have a region here and a region here. I have 2 bay regions for this particular molecule. So we would be particularly concerned about consuming this molecule, lest it act as a carcinogen. So this is a nice sample molecule of a polynuclear aromatic hydrocarbon that both belongs to an important point group, is centrosymmetric, and last but not least, it demonstrates not one, but 2 of these critical bay regions. It demonstrates not one, but 2 of these critical bay regions.